Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 48, part A. We are entering into section 5.5, which is called the functions of normal random variables. This is part 1. In the previous section, 5.4, we talked about using the moment generating function to transform random variables, specifically some combinations of random variables, such as s sub n is equal to x1 plus x2 up to xn, and xi is independent of xj, where I is not equal to j. Remember that xi is dependent on xi because they are the same. Okay, so they are not independent. Xi is not independent with itself. But when these variables are not the same, then they are independent. And so we showed using the moment generating function how to transform this quantity. And then we did a corollary where we assumed that they were IID. These are just independent. S sub n here is just independent. In this corollary, we assumed that they were independent and identically distributed. We did some examples. Then we talked about the theorem that was in the book that was an extension or generalization of the first theorem, where we talked about the linear combinations of random variables. We did the corollary for x bar, which you have to prove in homework, and then some examples. And in both cases, for both theorems, both examples, all these examples, we came up with some very important results that you'll need to know. Okay? You don't want to have to derive them or hunt for them when you're doing the final exam or the test. In this section, we're going to do a corollary to the bivariate transformation theorem. Okay? And it's called the convolution formula. So it's a special case or a special notation here that people like to use. And then there's a theorem that we're going to cover on the linear combination of the normal random variables. There's a corollary that goes with it, some examples, and then we're going to prove it with a theorem that x bar and s are independent. And then we're going to show the distribution of this very important quantity that we will use many times, especially next semester. Do an example. We're going to use we're going to do a derivation of students' t distribution, which is very important. It's probably the second most important distribution in statistics behind the normal distribution. And then the properties of t, the t distribution, and some examples. So let's get started. Before we get started, though, we need to remember that back in section 5.3, we talked about the properties of a random sample. And we said that a random sample was independent and identically distributed random variables. And we said n of them. And we calculated the expected value of x bar and s squared. And we said that both of these are unbiased estimators of the population or distribution parameters. Okay? But it turns out that s is slightly biased, but it's still one of the best, if not the best, estimator for the population standard deviation. There are others that are unbiased, but they're very complex compared to S. And the improvement is not very much. So now the results from there was that the first one is that the expected value of x bar minus mu is 0. That's because the expected value of x bar is mu. So we have mu minus mu is 0. And similarly, for the variance, sample variance, E of s squared, the expected value of s squared is sigma squared, so we have sigma squared minus sigma squared, which is 0. We also showed that the variance of x bar is sigma squared over n, and I provided you the variance of s squared because you will need that in the next semester. So it's good to have that information. Now, in section 5.4, we showed that if we had n standard normal random variables, IID, standard normal random variables, then the sum of the squares of those random variables is a chi-squared n. And Similarly, if we go back from a standard normal to the regular normal that are not IID, but have different means, different variances, and then we make a transformation called a Z transformation, so we take xi minus mu I divided by sigma I, then this becomes Zi, and Zi, I don't have to put the I there because they become Z, I, they're IID, there we go, IID standard normal. Okay, so then using the result from here, the sum of these transformed xi minus mu I over sigma I squared, the sum of those is again a chi-squared with n degrees of freedom. Okay, just like it was here. And then these were based on the fact that we had used the transformation theorem in 5.1 to show that if x is normally distributed with mean 0, variance 1, or a standard normal, then x squared has a chi-squared distribution with 1 degree of freedom. So let's talk about this convolution formula. Let's say that x and y are independent, and x has a distribution or PDF f of x, and y is distributed by PDF g of y. Then the PDF of z, which is x plus y, where v is equal to x, is given by the convolution formula, and here it is. So we have the f of z, which is the PDF of z, or the marginal of z, is the integral of g of z minus v times f of v dv. We're going to prove this using the bivariate transformation theorem. So let's start that. So we're told basically what we have to use for the transformation. Z is x plus y and v is x. So the inverse transformation for x is equal to v, or you could write this h1 of v and z is equal to v. And then we use y, we solve for y here, and we see that y is equal to z minus x, but x is v, so we have y is z minus v, or h sub 2 of vz is equal to z minus v. Now, we're going to use the transformation theorem, so we have to find the Jacobian. So the Jacobian is the determinant of the matrix given here, where we take the partial derivatives of h1 with respect to v, and then with respect to z, and then h2 with respect to v, and h2 with respect to z. When we do this, you'll see that we get the partial of h1 with respect to v is simply 1 because it's just v. And there's no z in this function, so the partial with respect to z is 0. And for h2, the partial with respect to v is a negative 1, and the partial with respect to z is a positive 1. To calculate the determinant, we take the product of the forward and downward diagonal, subtract the other diagonal, and this is for a 2 by 2. So 1 times 1 is 1, minus 0 times negative 1 is 0, so 1 minus 0 is 1. And this is positive, so the absolute value of j is also positive 1. Now, the joint PDF of x and y is easy because they are independent. So we just simply take f of x times g of y, and that's going to give us f of x and y. Now, by the transformation theorem, the bivariate transformation theorem, the PDF of z and v is f of zv, and this is given as f of h1, h2, so the joint distribution of x here, h1, h2. So for x, we're substituting in h1, and for y, h2, times the absolute value of the Jacobian. And so here is our expression for the joint PDF of x and y. And so x only shows up in f, and y only shows up in g. So we make the substitution for h1, so for x, and that leaves us v, so f of v. And then y is z minus v, so we have g of z minus v, and then times 1, so we're left with f of v times g of z minus v. To get the marginal of z, we have to integrate with respect to v, this joint PDF. So this is f of z and v here. And so we take that, we integrate it with respect to v to get rid of the v's and are only left with z. And we see that we have the convolution formula here, g of z minus v times f of v times dv integrated across v. So that is the proof of the convolution formula. Please make sure you have that handy. You might need it, that convolution formula. Now, let's look at another theorem where we have x1, x2 to xn are independent, normally distributed random variables. Each have a different mean and a variance, or they can, mu I and sigma I squared. Then the linear combination of ci xi, so the sum of ci times xi, where ci is just a constant or real number, it has a normal distribution with mean ci mu I, the sum of ci mu I, and variance, the sum of ci squared sigma I squared. So let's prove this. To do so, we need to recall that the moment generating function for a normal distribution, so variable x sub I, is n, yes, that has a normal distribution with mu I and sigma I squared as the mean and variance, is m sub xi of t equals mu t, so I should say mu I. If I'm going to use the I there, I need to use it here. So mu I t plus sigma I squared t squared over 2. Okay? And t is from negative infinity to positive infinity. It's a real number. Then the MGF of ci xi has a normal distribution, ci mu I and ci squared sigma I squared. How do we know this? We take the expected value of ci xi, that's going to be ci times e of xi, which is ci mu I. And the variance of ci xi is equal to, we square and remove the constant, ci squared, variance of xi, and that is equal to ci squared sigma I squared. And so that's how we know that this has a normal distribution with mean ci mu I and variance ci squared sigma I squared. And the MGF for this will be m of x sub I of t. And so instead of writing e and then putting all this in the exponent, I wanted to make it a little easier to read. So I used exp, and then we have ci mu I in place of mu times t. And then we have ci sigma I, quantity squared, in place of sigma. And that's times t divided by 2. Now, the range of CIT is, we just substitute in that for xi, right? And so that's between negative infinity and positive infinity. If we divide by a constant, we're still going to end up with t between negative and positive infinity. And then we're going to use Theorem 5.4-1 to write the moment generating function of y, which is, remember, y is this linear combination ci times xi. And so the moment generating function of y of t is m of y sub y of t is the product of m sub xi ci. And we're taking the product from I equals 1 to n. And so we're going to substitute in the moment generating function, the expression here, and we get mu e to the mu I ci times t plus sigma I squared ci t squared. Now I have rearranged these from where I wrote it here. Here I had sigma I ci sigma I squared, and I forgot my t squared here. And so this is, of course, ci mu I t, and this is ci squared sigma I squared t squared over 2. And so I can rearrange, and that's what we've done here is we've rearranged CI with T. And so this is, again, well, we did that to show that this was CIT here. But we've expanded that without the parentheses, and then we've said that, okay, we need to set this equal to mu, and we need to set this equal to sigma I squared, or to sigma squared. So this is sigma squared, and this is mu of our new distribution. And so this is the EXP sum of mu I CIT and t squared over 2 sum of CI squared sigma I squared, and that is the moment generating function from our normal distribution with mean, sum of mu I CI, and variance, a sum of CI squared mu I squared. Where did we get this? Where did we get this here? Well, we took all of these and we wrote them. We took everything here and we wrote out the product. And when we wrote out the product for I equals 1 and then I equals 2, then we added the exponents and we ended up with the sum from I equals 1 to n of mu I CI and for the mean. And then over here we ended up with the sum of CI squared sigma I squared from I equals 1 to n. Okay, so here we have the mean and the variance using the MGF formula, and so we have proved that this has this normal distribution here. All right. The corollary says, let x1 to xn be observations from a random sample of size n. So we have n random variables that are IID. And they're drawn from a normal with mu sigma squared distribution. So they're IID, they have mu as a mean, sigma squared as a variance. Then x bar has a normal distribution with mean mu and variance sigma squared over n. So let's prove this. Let CI equal 1 over n. Then using our theorem above, we have the sum of mu I CI is the sum of 1 over n times mu. And 1 over n is a constant with respect to I. In fact, mu is too, but we'll just pull this out into the front. And then we've got the sum of mu from I equals 1 to n. Now, this is going to be mu plus all the way up to mu, and there's going to be n of these. That's what this term here is equal to. And so this is equal to n times mu. And so we have 1 over n times n, so those cancel, times mu, and so that leaves us with mu. Okay? And we have the sum of CI squared sigma squared. Okay? And we don't have an I here, so we can pull out, let's see, we had, what did we miss? So CI is 1 over n. Okay. So I pull out, so this is CI squared, sum of, from I equals 1 to n of sigma squared, and CI squared is equal to 1 over n quantity squared, sum of sigma squared, and this is 1 over n squared, and this is n times sigma squared, and so this cancels with that, and that leaves me sigma squared over n. And so that's what we have here, and so x bar has a normal distribution with mean mu and variance sigma squared over n by this above theorem. Okay, so that's it for this video. Please don't forget to scan and upload your lecture notes before midnight, the date listed on the course calendar. If you have questions, come to virtual office hours. If you need an answer before you can make it to virtual office hours, then by all means email me. I'm happy to help you, but you'll need to email me a picture of the problem and a picture of your work so far I may not have access to the problem, and I can right away, and I can see what you're doing. That will help me guide you towards the right solution. So I hope you will take care of yourself, and we hope to see you next time.